After studying this module, you shall be able to know the limitations of first law of thermodynamics, learn about some thermodynamic terms required for second law of thermodynamics, know different statements given for second law of thermodynamics by different scientists. The original statement of the second law of thermodynamics is much concerned with the development of the theoretical aspects of heat engines, especially the Carnot cycle. The second law of thermodynamics states that processes occur in a definite direction, while the first law does not focus on the direction of the processes. That is, the direction of a particular spontaneous transformation can be ascertained with the help of the second law of thermodynamics. The process which satisfies the first law does not mean that it will definitely going to occur. Thus, there is a need of another principle which can identify whether the process will occur or not. Before discussing about the second law of thermodynamics, the limitations of the first law will be discussed. Now, we will see the limitations of the first law of thermodynamics. The first law of thermodynamics gives the definite relationship between the heat absorbed and the work done by the system in a given process. But the direction of flow of heat was not stated by this law. According to this law, extraction of heat from the ice is not possible by cooling it to low temperature and then using it to warm water. While from the experience it is known that it is not possible to transfer heat from the low temperature to high temperature until some work is done, while the heat flows from the high temperature to the lower temperature on its own. The first law states that in an isolated system, the energy does not change during a specified change of state, but it does not give any information about the specified change, that is, whether the change will occur spontaneously or not. According to first law, the total energy of the system remains conserved, that is, one form of energy can be completely converted into another form of energy. But Joule's experiment has shown that the heat energy cannot be completely converted into work energy, while the work energy can be completely converted into heat energy. Thus, heat energy and work energy are not interchangeable forms of energy. Thus, there is a requirement of another law, that is the second law of thermodynamics. The second law of thermodynamics gives the direction of a spontaneous process. It introduces a new concept of entropy that governs the criteria of spontaneity. Before discussing about the second law of thermodynamics in detail, some terms should be understood first. We shall see some definitions for expressing the second law of thermodynamics. They are as follows. Heat reservoir. It is a large system which is in stable equilibrium and heat can be transferred to and from it without any change in its temperature. The heat reservoir, which is at high temperature and from which the heat is transferred, is known as heat source, while the heat reservoir which is at low temperature and to which the heat is transferred is known as heat sink. Work reservoir. It is a very large system in which stable equilibrium through which definite amount of work is transferred adiabatically without any change in pressure. Thermodynamic cycle. If the system, after undergoing series of processes, reaches to its original state, then the system is said to have completed a thermodynamic cycle. In this, the properties of the system at the beginning and at the end of the cycle are same. Thus, Pf is equals to Pi, that is, pressure of the system at initial or beginning stage and at final or the end stage is the same. Similarly, Tf is equals to Ti. Heat engine. It is a thermodynamic system working in a thermodynamic cycle to which net heat is transferred and from which work is delivered. Thermal efficiency neta Th. It is the measure of performance of the work producing device. It is given by the ratio of net work, which is the desired result, as an output to the heat input, which is the cost paid to obtain the desired result. That is, neta Th is equal to desired result divided by the required input. Thermal efficiency is always less than 1 and can also be written as neta Th is equal to W net out divided by Q in, where W net out is the net work done and is given by W out minus W in. Heat pump. It is a thermodynamic system which operates in a thermodynamic cycle and transfers heat from low temperature body to high temperature body. In transferring this energy, the heat pump receives energy in the form of heat or work from the surroundings, while the refrigerator is a device which operates in a thermodynamic cycle and extracts heat from low temperature body. Now we shall look at various statements of the second law of thermodynamics. The second law of thermodynamics is expressed in many ways, the most salient statements being given by Rudolf Clausius in 1854, Lord Kelvin in 1851, Max Planck in 1926, and so on. Although these statements are different, but each one of them predicts the direction in which a change will take place spontaneously. Now we shall discuss these statements in detail. The Clausius statement of the second law. The second law of thermodynamics was founded by the German scientist Rudolf Clausius in 1850. He developed the relationship between the heat transfer and the work done. His formulation of second law is also known as Clausius statement. The concept of passage of heat was used in Clausius statement. This statement states that it is not possible to construct a device that operates in a cycle and develops no effect other than the transfer of heat from a low temperature body, that is cold region, to a high temperature body, that is a hot region. In other words, heat cannot transfer from cold regions to hot regions spontaneously until some external work is done on the system. For example, in a refrigerator. Clausius also said that the entropy increases towards a maximum and the energy of the universe is constant. The Kelvin statement of the second law. This statement for second law was proposed by Lord Kelvin. It states that it is impossible to construct a device operating in a thermodynamic cycle to receive heat from a single heat source and produce the net amount of work. It also states that it is not possible to derive mechanical effect from any part of the matter by cooling it below the temperature of the coldest of the surrounding objects. If the system violates the Clausius statement, then it will also violate the Kelvin statement and vice versa. Thus, both statements are equivalent. The Planck statement for second law. Planck states that it is not possible to construct a device which will operate in a complete cyclic process and produce no effect except increasing of weight and cooling of reservoir. Carnot's principle for second law. Carnot's principle was proposed by French engineer Nicolas Sadi Carnot. He was the first who studied the principles of the second law of thermodynamics. The concept of cyclic operation was also introduced by him. Carnot's principles refers to a cycle of Carnot engine which is working in a quasi-static mode so that the transfer of heat and work takes place between the subsystems which are always in thermodynamic equilibrium. The efficiency of reversible Carnot cycle depends on the temperatures of the two reservoirs and is the same whatever be the working substance. The Carnot cycle consists of 4 reversible processes, that is 2 isothermal and 2 adiabatic, and will be discussed in detail in the next module. Now we shall look at a numerical. Calculate the cycle thermal efficiency and the amount of heat released by the cycle to the surroundings if the steam power plant produces 50 megawatt of net work while burning fuel to produce 150 megawatt of heat energy at the high temperature. The solution is as follows. The thermal efficiency is given by neta Th is equal to W net out divided by Q in. Substituting in the above expression, we get neta Th equals to 50 megawatts divided by 150 megawatts, which is equal to 333 or 33.3%. W net output will be equals to QH minus QL, or QL will be equal to QH minus W net out, which is equal to 150 megawatt minus 50 megawatt, that comes out to be 100 megawatt. Thus, thermal efficiency is 33.3% and 100 megawatts of amount is released to the surroundings. Now, we shall summarize what we have learned in this module. The first law of thermodynamics does not give any information about the direction of flow of heat. That is why there was a need of the second law of thermodynamics to give such information. If the system, after undergoing series of processes, reaches to its original state, then the system is said to have completed a thermodynamic cycle. In this, the properties of the system at the beginning and at the end of the cycle are same. Thermal efficiency. This is always less than 1 and can also be written as neta Th is equals to W net out divided by Qin. Clausius statement for second law states that the heat cannot transfer from cold regions to hot regions spontaneously until some external work is done on the system. Kelvin's statement states that it is impossible to construct a device operating in a thermodynamic cycle to receive heat from a single heat source and produce a net amount of work.